No, I'm John Hahn. I'm the Deputy Director here at AROS, filling in for Pete Doucette, who's on travel the last week and this week. And so this week, or this month on our seminar series, we're going to be talking about LANDFIRE and remote sensing based disturbance mapping. And Sanath has agreed to do the seminar this month, and it's one of the ones that personally I find very interesting because of the LANDFIRE being such an impactful application in science for the country, that everybody can see the impact there. And Sanath has a background in physics, and he specializes in developing remote sensing algorithms to help quantify environmental and biophysical variables. He developed a lot of novel remote sensing methods for improved characterization of wildland fires and land surfaces for his doctoral and postdoctoral work. He's now the senior scientist with the Arctic Slope Regional Corporation, the ASRC folks here at AROS, and he supports the LANDFIRE Science Support Services contract and the LANDFIRE team. It's a multi-agency team, actually. And so his duties include developing and advancing some remote sensing algorithms for LANDFIRE applications. And so Sanath is going to walk through some things here, and I've asked him to keep it at, I said keep it at someone as stupid as me level, but he said he couldn't go that low, but he would try to keep it up at a level that he's not talking about bits and bytes and pixels and things like that. But for any of the scientists that are on, don't be afraid to ask him technical questions. And if he doesn't have time or doesn't want to address it here, he'll get back to you at any point and discuss it further. This is a passion for him, and I assure you that he loves exchanging information on this and talking about it. So with that, I'm going to turn it over to Sanath.
Hey, thanks, John. I hope, yeah, I'm alive. Yeah, I guess so.
Yes,
thank you, John.
You are.
Yeah, thank you, John, for the wonderful introduction. And before I start, I think I would like to give a shout out to all my colleagues and collaborators. Definitely Josh Picott, along with, he's also a fellow scientist at the ASRC for the science contract. And Brian and Ray, these are the people doing the heavy lifting. They batch process the data. And a big shout out to Paul, Jacob, Karen, Lucas of Reno, and Claudia, because these are the analysts. And in this talk, I'm going to talk about some of the enhancements to the LANDFIRE remote sensing based disturbance mapping. But a lot of lessons learned is coming actually feedback from the analysts. And shout out to Erica, who's actually kind of doing some help with the scripting, and Inga, who's like the team, the scientific lead, technical lead in the LANDFIRE from the TSSC. From the government side, Birgit Peterson has been there with us for a long time, and now she has moved to other jobs. And Tim Hatton is now our program manager. So with that, I represent the work of all these people. It's not just mine alone. And yes, I've tried to keep as an open audience, and I've tried to keep it as more of as a 101 level for everybody's benefit. But if you have any deeper questions, I think as you mentioned, we can go deeper later. Okay, so without much ado, let me quickly jump into what's LANDFIRE, the mission and objectives. As John pointed out, it's a landscape fire and resource managing tool program. It's a shared program between multiple government agencies, including the Wildland Fire Management, the USDA, the Forest Services, and of course the Department of Interior. And LANDFIRE is the first nationally consistent collection of spatial resource data set, which has an ecological foundation. And the main purpose it was supposed to be useful across many disciplines. So the objective is very clear. It's to generate some products which define the vegetation, the fuel conditions, or the ecosystem conditions on the national level scale and being consistent. And the intended applications is, of course, as the name suggests clearly, it's a fire hazard mitigation in terms of fuel reduction and incident planning, or it helps in the national strategic planning, any kind of ecosystem restoration, or if you want an environmental management applications, I'm pretty sure the LANDFIRE data kind of finds applications. I'm not going to dive into depth about the product suite. We have an extensive list of products, but what's more interesting is other groups and users have used some of our products to generate their own next generation of products, which are useful for their purposes. Talking about the users, I quickly look for the users' demographics. As you can see, we are a very diverse group of people who use the LANDFIRE data. And although the names such as LANDFIRE, we do actually all lands and all kind of vegetative definitions on all lands in their conus and conus. A majority of the users are coming in from the .com and the .business sites, but a significant chunk is actually coming from the government side, and of course the non-profit and the universities. So these are our heavy users, and we need to provide them with a very high quality product which has a high accuracy and a low latency. We did a survey of the users on what they use some of the data for. As you can see, the bulk of the data is used for something to do with fire. The next bulk comes with something to do with vegetation. That's exactly the kind of data we have. And of course, the more talk will be concentrated on the disturbance today. We'll talk about how we map it, how we use remote sensing methods to disturbance mapping. So before I jump into remote sensing, I know most of you are familiar with remote sensing, but just a quick refresher just to see what you're talking about. Remote sensing is basically using the vantage position in space to observe land surfaces. So we have, in particular, I would like to talk more about, I would like to highlight the importance of these polar orbits where a satellite is going from south to north or north to south. A key advantage in such an orbit is the sun is always behind your back. What it means is the satellite is transiting a given land surface at local noon. Local noon implies lower number of shadows, more brighter surface, and you have more information about the land surface. And when it comes for the revisit, the sun angles are preserved. So with the result, you're actively able to compare one image with the other. Now contrast this with other lower Earth orbit photographs, which one might happen during the daytime, or one might happen towards the late evening where the shadows are long. And it's not that very easy to compare photographs where the sun angles are different, because the shadows will not be able to, you'll have to reconcile the long lengthy shadows. So that's a huge advantage in using a polar orbit. The satellite which I showed you was the MODIS Aqua and Terra. They go around the Earth, but most of the polar orbits, they go roughly around 90 minutes and they cover the Earth in swaths. And of course, clouds is always a pesky problem. They get into the way. But with multiple orbits, you can composite them and you can actually generate a cloud-free composite. This is a cloud-free composite generated at 500 meter level using the MODIS Aqua and Terra. But the same thing can also be done at Landsat. Now, we start seeing the Earth in its true structure, the way without any clouds, unimpeded, and we can actually see its breathing. This is a whole annual time step. So this is the kind of data which we use. But what does a satellite observe? Conventional cameras observe in the RGB, in the visible wavelengths, which is roughly in the lower part of the spectrum here. But then most of the satellites, which are reflective wavelength observations, can observe it to the NIR, the near infrared region, the software infrared, and the higher software infrared regions. Some satellites go all the way till thermal, including the Landsat. That's in the 10 micron, 11 micron bands. So why do we observe in different bands? Well, we get a lot more information. For example, if you observe the vegetation in the NIR bands, you can see that the vegetation signal is much higher. So observing in the NIR bands will actually give us a very strong signal for vegetation. So if there's any disturbance that happens on vegetation, NIR bands will be the first one to respond. And if it drops, then you know that what kind of, and each of the classes, the land cover, they have what's called spectra. You can see it as a fingerprint. And each fingerprint for different classes is different. And we use this information to diagnose or to detect what kind of land surface exists or if something has happened to it. So we use these basic concepts of science to do our LANDFIRE mapping. So the first thing we do is actually we create a base map. When you want to create an all-field map across the conus, we create a base map, and that base map takes quite a bit of resources for us. We use the Landsat imagery along with a lot of ancillary data, and we model the vegetation that exists at that particular pixel or particular location. Since that is a very intensive task, we don't come at a base map every year. The last base map was in 2016. But what we do is after we generate the base map, we look for places that have changed. Because just for a number, that looking at the entire conus surface, less than 1% of surface of the conus changes or has a vegetation which is getting disturbed. So there's no point in mapping the 99% again and again. It's a little easier computationally, and we can target our resources to those places where we change, and we can do a better job for what has changed. So that's the philosophy behind why we use a biannual update and we create a base map. Of course, things are changing. We are even progressing towards making a base map every year. Okay, so what do we map and how do we map? as I talked to you before, this is a spectrum of a typical spectrum of soil, dry vegetation, and green vegetation. And the RGB we observe here, that's basically the true color composite. But if we change our green channel to something in the near infrared, and we call this the new false color composite. So from visually, we trick our brain into observing signals which are very strong to green. Things look that very green are basically vegetation. And anything that does not look in green is something that has happened to vegetation. So that's a very simple way an analyst or anybody else who is using remote sensing on a visual way, they can use a false color composite and take the advantage of the power of observing the near infrared for directing vegetation. In this case, we direct the vegetation fire, or it can be a harvest. So in a nutshell, we kind of map both basically that management activities and of course the natural process as a disturbance, and we try to map it. Going to how we use these methodologies for change detection is we kind of compare some of these composites from consecutive years with the same anniversary dates. The same anniversary date is very important because plants do have a phenological cycle. They grow, they have a plateau, they senesce, and then they die off. They have a phenological cycle. So if you compare a plant from, or if you compare a vegetation from early spring to a late spring, there will be spectral differences, but that's not necessarily a vegetation disturbance. So you want to consider the same thing from a same phenological state. And if you recall, I was talking about the orbits of the satellites, and usually with the anniversary date, the sun angle is also the same. So you have much less of the viewing angle changes that can happen. So you have these two images now which you can compare, and that's why the quality of the Landsat data is extremely important, because we have a close to the anniversary date, and then we have a very well calibrated data, so we can compare a particular day from 1 year to the corresponding day in a different year. Of course, we have to assume that there's no atmospheric effects. Those things can also compound your change detection. Disturbance may not always have a spectral contrast, right? For example, if a leaf falls off a tree, is that considered a disturbance? Will it have a spectral contrast? And in the same way, all spectral differences which are observed are not necessarily vegetation disturbance. Like, what if there's a cloud which was not labeled correctly? What if there was a cloud shadow that was not labeled correctly? What if there was some kind of a thick aerosol that blinds you and that causes a spectral change? So these are the natural variabilities which we need to reconcile with before we design a change detection system. So just to simplify how we do it, I'm going to imagine that we have a single dimensional feature space. So the natural variability is a perfect Gaussian. That's how everything in the universe is, right? So our assumption is absolutely valid if you want to parameterize it, and it follows a nice Gaussian. And now imagine another distribution of a disturbed surface, which follows another beautiful, nice Gaussian curve. And you can clearly see that once we start, when we start putting a cutoff, when we define saying that, hey, anything beyond that particular value in this feature space is class 1, and anything that is beyond this class is the class 2, we tend to start getting into the overlapping zones where we have made a mistake of whether we are either omitting certain classes or we are including some classes from the other class. So the omission error and the commission error is kind of very inevitable every time we use any hard threshold cutoff in a single feature space. So how do we avoid this? Well, we look for convergence in other feature space. Like, as I showed you before, in the NAR will change, and so does the red channel change. So if you use multiple feature spaces, maybe we are slightly better off. And why just use multiple bands, or basically in spectral observation, we can also use what's called indices. Indices are basically ratios of observations in different bands, and they do have a slight advantage. They are a little more immune to topographic effects, and they're a little more immune to atmospheric effects. But the fundamental question still remains, how do you define these cutoffs? Who defines these cutoffs, and what is an ideal cutoff? Because you can always play with these cutoffs for either a low emission or a higher commission, or a higher commission and a lower emission. You cannot have the best of both worlds, and that seems to be a very inevitable fact. But people have gone around it. Multi-index integrated change analysis that was designed and developed by our own Suming Jin. She's now for the NLCD program, the principal scientist, I think. She developed the bitemporal change detection algorithm. And the way she detects it is, again, use 2 Landsat images from 2 different eras, and we're going to compare them. And to define the cutoff, make a very fundamental assumption. Changes don't happen all the time. In fact, if you recall, 99% of the lands don't change. At least that's what the data shows. And the change fraction is definitely less than 1%. So if we are able to draw some kind of a large data means, so those means are usually robust, and any statistical summary can be used to remove the outliers. So In terms of multiple integrated integrated change analysis, which we fondly call MIICA, that is defined on the tile level, and she uses DNVR, the DNDBI, the CV, and the RCB max. We can go into the detail later, but for all practical purposes, these are all different feature spaces. And so she defines these cutoffs from a big tile, and it is shown to be pretty good for corners-wide applications. From the LANDFIRE perspective, we have kind of slightly modified the same MIICA. We not only use it for just 2 images, we use 2 seasonal composites. We use it during the leaf on state, and we also use it during the leaf off, so the early spring and the late fall. So we use 2 different composite dates to make sure that our images are cloud-free, and we do a change direction between these 2 images. And those images are then combined by the analysts. They are reviewed by the analysts and make sure that whatever we see as a change, or it's a change that happened to or a disturbed vegetation, and not anything else, and is not an artifact of observation. So in a way, which we differ from many other mapping programs, is we do have an analyst at the back end of system, because the disturbance basically feeds on to the other LF product suite. And so we have to ensure that a very high quality is maintained when we do our change detections. So they are principally tasked with reducing the commissions and, of course, the omissions. So what is so special about a human where the computers are struggling? Like, if I had shown you this image without even priming you about what the green means or what the red means, immediately you would have picked out that there are certain places which are consistent, or they are not changing. There are things which are changing. There are things which are changed. And there are things which are kind of shades of greens are changing too, but we don't know what it is. So this kind of information which our brain can immediately conjure up, because we use a very contextual, the spatial context which we use. Now, unfortunately, the computer vision, we have still yet to reach the state where the spatial context is very easy to achieve, because to know the spatial context, we need to know what is disturbed to know its background. So it's a kind of an iterative process. It's computationally very extensive. But these days, with the reducing cost of computing and increasing computing power, these things can be easily achieved. So in this one, you see that there are some obvious changes. You also see some changes in terms of greenery, which are possibly artifacts of the atmosphere. And you also know that these are changes, and some of these changes are not related to disturbance in vegetation. So this is something which a human can easily decide, but computers don't easily do it. Another important aspect where the human helps is the ability to adapt to a very local circumstance. Even despite the fact that we use composites, they can tweak the change. They can see what defines a change, and they can literally play at the level of the noise level. And unlike a fixed thresholds in many of the algorithms which we use, they can use their spatial context to know that, hey, okay, fine, these are very strong, high contrast changes, but there are some subtle changes, and they are able to actually map out. And these are the things which will reduce our omission errors. And I will show you an example where the analyst also plays a very important role in lowering some of these omissions. So the big question now comes: can we fully automate these processes? Well, here's our attempt. But before we go, there's a very famous quote by a very famous scientist, and the challenge is probably if you can identify who said this. The holy grail of change detection is still the total automation and high accuracy. They got the first part pretty correct. And however, the methods that reduce labor costs while maintaining consistency and accuracy are needed. And this is where I think we are closing the gap, and a lot of programs have done this. LCMAP, for instance, LCMS, for instance, they are closing the gaps, and we're also trying to. The LANDFIRE is also trying to use many of the modern techniques so that we can come closer to the holy grail. And if I didn't see in chat, oh, I did see some, I'm not sure. That's our very own Tom Loveland, Terry Saul, Steve Steveman, Zach Gallant, Christy Slayer, and Daryl Napton. They're all, most of them from Eros. And they made this, they had this quote about 20 years back. A little sad to say that the first statement kind of still hold, but we've done a heck of a job with the second one. And we are coming close in this 20 years. So that's what I'm trying to try and convince that what we have done for the LANDFIRE disturbance mapping method. So just to recap, what happens in an automated change detection system is if you kind of define a threshold for anything. It can be a time series change detection, it can be a bitemporal. They usually defining something as a natural variability and something called an outlier. So you tweak one, either you inflate the omission or you inflate the commission, and correspondingly it will have the reverse effect on the omission and omission errors. So that is something which is very inevitable. And somehow we see that the human perception, the human vision, equation is very easy. We man evolved possibly to look for a predator in the wilderness. We can identify a very small change very easily, and I'm not sure how well the computers can mimic that particular gap. However, a lot of successful land monitoring programs have shown that the gap is still narrowing. We are way better off than where we started 20 years back. So from the rest of the talk, I'm going to be trying to talk about how the two big things which I feel as what helps the human perception a little more superior when it comes to image interpretation can be exploited for our purposes. One is definitely learning. Like, you know, the human, we can adaptively learn and we can change to the changing situations. So we are not kind of a little hard-coded or fixed. The other one is more of a vision problem, is a spatial context. Unlike just looking at one pixel drilled down in time, we can look at the spatial part of what's happening, because what happens in space, if no disturbance is an isolated event, they're usually contiguous in space. So spatial context can be an extra piece of information that can also help us decide whether a disturbance is a vegetation-related disturbance or not. So what we need to do is we just need to train the machine very carefully. And if you give it enough, machines really do well if you have a full census of the phenomenon of interest. But of course, as you can see from some of the example here, the training machine is not easy. Like, you know, try counting the number of muffins or try to count the number of puppies here. Things look very similar, and you need to use a little bit of context to even decide whether it's a muffin. And even for a human, this is not that easy. But once we have this kind of a training data, we can teach a machine, but then it would respond within the domains of the training which we have given. So we need some very diverse and rich training data. So that is the fundamental thing which training a machine needs to learn to predict the disturbances. Hey, but we do have an analyst review data, and we do have a fairly high confidence that these are fairly low omissions and fairly low commission errors. And as we talked about the satellite data, we can create a whole suite of predictive variables. Each observations can be used as a predictive variable, both its band and its indices. So what about the spatial context? Is there a way we can include the spatial context? Because we just don't want to observe just one pixel. We want to know what's going on the side. And that was kind of research we did some help on. So, for example, how do we parameterize to feed a machine learning language the concept of spatial context? Imagine a kind of a space where if things green here, it's all green. Things that are brown is basically deforested or degraded vegetation. So you can define some kind of a loose threshold to saying, hey, anything which is not that green or a little more brown, you can define some feature space, and you can come up and you can demarcate in a loose way, which will overestimate the area, and we call them as disturbances. That's what we say, that we can lower our thresholds or liberal thresholds to lessen our omissions, but now we are inflating our commission errors. Then what we do is, to get the spatial context, we consider the rings around them, each unique rings. And the philosophy behind this is, if there is a disturbance, its immediate neighbors around it are representative of the pristine conditions. So if we are able to parameterize them, like for example, you take the mean and the standard deviation, and if we compare each of the pixel inside the disturbance, that kind of gives us what's called a spatial change probability. So we can now create a new map, which basically tells you how different those pixels are with respect to their own neighbors, which are individual and unique neighbors around them. Like, for example, what you see, the core regions are shown in red. That means they are 3 sigma and higher. That means they are very different from the neighborhood. And the edges are kind of more towards yellows and grays, which are basically 2 and 1 sigma, which suggests that they are less and less change compared to the neighborhood, which is very logical and very convincing, because in any kind of a disturbance, the disturbance is usually core. And as you go towards the edge pixels are mixed between a disturbed pixel and an undisturbed pristine neighbor. So those effects will be less subdued. So you do expect the core to be a lot more different than the edges. So we know we are getting somewhere, but we don't do it at one disturbance. Now here's where the sheer computing power comes in. We do it for a hell of a lot of disturbances. In our case, we do it for both biomass decrease that's shown in red, and of course the biomass increase which is shown in green. And we look at each of the individual neighborhood. We draw individual circles and we use the statistical summaries. And then we come up with this map, which is now shown in grayscale. So the darker which is there, it means that more spatially divergent and different they are. So the red zones are the places where you saw those disturbances. And if you can pay attention, some of you who are good at image interpretation would have immediately guessed that these are perhaps topographic effects which are causing this things to be directed as a change. And what we clearly see is changes which are really, really significant, or which are very, very spectrally very different. They're also spectrally different from the neighbors, and these things show up strongly as very high z-scores. But again, we come to the same problem. Who defines this cutoff, and how do we ever come out of this point? Like, if we define a cutoff of one place, we're going to have a very different cutoff for a different place. And I think this is where the machine learning comes in. And as we talked about, we do have access to a lot of predictive variables, which are basically the LANDFIRE, the Landsat series observations. Landsat observations go from all the way from blue to shortwave infrared. We ignore the band 1, the coastal aerosol, because it's the changes are usually due to the atmosphere and not because of the land surfaces. But we use the TOA, which is basically stands for the top of the atmosphere. So we use all the 6 bands of Landsat 8. And we use 3 years. We bracket the changed year, both the year behind and the year forward. And the reason why we do that is we now have a more complete, robust idea about what the pre-disturbance conditions are and what the post-disturbance conditions are. And that way, when you feed it to the model, it's able to predict a lot more accurately. We just don't use it the top of the band atmospheric reflectances, which we see. We also use indices. If you recall, when indices are nothing but ratios between those bands, they are slightly more immune towards topographic effects and sun viewing angles. But on a more bigger advantages, sometimes they define, like for example, the NDVI is defined to detect changes in chlorophyll, or NBR is definitely changed. It's designed to see for differences in vegetation. So we have a suite of predictive variables, and we also have this delta indices, which is basically the difference between the time 1 and time 2, and we use it for 2 different seasons. Along with our z-scores, we come with a total of about 73 predictive variables, and so that's a long list of variables which we have, and we also have our analyst review data. So we can now start looking at, we can train the model using 1 year, and we can predict the model for the target mapping year. So we call that a SAFER. I want to mention, which it was actually a spatially adaptive filter for error reduction. So I'll be frequently referring to it as a SAFER from now on. So the SAFER flowchart essentially has, we start with the multi-year Landsat data, and we create our interim disturbance products, which includes the MIICA, which also we adjust the DNBR, and we make sure that we include a little more than, we kind of tweak so that we have more commission errors, but we have less omission errors. And then we generate a list of predictive variables, and we also look at the previous year's analyst reviewed disturbance data, and we mix all these predictive variables and the previous reviewed analyst disturbance to create this random forest. And once we train this random forest, we assume that the spectral signatures, the causalities, the correlations between the spectral observations and the disturbance are maintained the next year. So that is an implicit assumption. And we now do the same thing for the target mapping. We again create our interim disturbances using MIICA, and we change the threshold for DNBR based on the analyst experience, and we create the seasonal composites, which gives you the entire suite of predictive variables. And we feed it to a random model prediction variable. Now, if Tom Loveland was wrong and we have created the Holy Grail, we would have got the perfect SAFER filter disturbance. But unfortunately, he's right. It's not 100%, but we are definitely getting there. It still requires a little bit of analyst review, but definitely a lot lower. And hopefully, Brian will be able to talk more about this. Brian Talk is actually presenting in Pecora, in a session led by Tim Hatton. And if you're attending the Pecora, please do attend this session. He'll be more concentrating about how the analysts review this data and how we are able to have a high accuracy standard of a quality control for the LANDFIRE disturbance products. So once the analyst review disturbance product is available to us, now it feeds in back, and so that we can now predict for the next year. So this is the whole flow cycle of how we map disturbances. So what kind of computational resource you use? This is kind of one of my favorite slides. It takes a hell of time for processing or staging the data itself. It takes quite a while. It takes about a day to process, download, and stage the 12 terabytes of data per tile we have for a given mapping year. And usually a tile has anywhere between 2 to about 5 million pixels, with a median closer on 3.7 to 4 million pixels. And we use a random forest training, which is basically the machine learning program. And we're kind of restricted with one node. The way random forest works is it looks for some kind of a correlation or a correlation between the predictive variables and your response variable. And if the node does not have a shared memory, we cannot use multiple nodes. So we are kind of limited to using a node using one node with about 40 cores or 80 cores as my node might handle, and gives you the 192 gigabytes of memory. So we are able to train random forest within that memory plot, and then we use a prediction. All the safer modules were written in C++ actually. Big shout out to Jeff Alou. Thanks for the image, Jeff, and also thanks for patiently answering my questions when I had process problems in making it optimal for parallel process. Even the Ranger, which is basically the random forest model, that's also based on C. It's available for R, it's available for Python. The biggest advantage is it's pretty fast. It's a very fast implementation of both random forest training and, of course, the random forest prediction. They're all optimized for using the HPC's high performance computing power. The bottleneck which we had was I used the R script as a wrapper for the C++ function, and Erika is now rewriting it, and hopefully we'll have a little more, we can handle a larger tiles and much larger disturbances. But as of now, after the compositing is done, it takes anywhere between 5 to 15 hours per tile. And finally, this whole 12 terabytes of data is distilled into 4 megabytes of disturbance data. Of course, it is about a gigabyte if you consider the composites, but the one mostly of relevance is this is what is fed downstream, because it contains just the place where the disturbances are, and of course the severity of the disturbances. So what did we do? How are we doing it? We just don't want to deploy the system and without testing it. So we did have a consultation with some of our analysts, and we looked out for, hey, where do we test this? That's part of the exercise where we decided on which test zones to test these algorithms. So what you see on the right-hand side is actually the base map, which is created in the remap 2016. And the black squares are the places where we have the LANDFIRE tiles. And the little gray ones are all the LANDFIRE tiles, the 98 of them throughout the CONUS. So we had all our statistics are defined, or our models are run specifically to any of these local tiles. If you look at the background, some of the ones which are light green, anything which is a little green, those are the places where there's a tree canopy, whether it's closed canopy or an open tree canopy. But then if you look at some other places which is more brown or a little more gray, they are shrublands or sparsely vegetated. And if you recall, the trees, they have a much higher vegetation signal, so it's a lot easier to detect disturbances in those places. But then the shrublands and the sparsely vegetated regions, the effort is a lot more to detect any small change, because the vegetation signals itself is not that very high. So we selected these things just to have an idea about how our safer algorithm will perform. And then we are planning to compare it with analyst review data, and that's what I'll be talking about quite briefly. So quickly, I don't want to show you with everything and how it worked or not worked. I'm just going to show an example of where it worked great, and of course where it completely flopped, and then for the reasons why. So this on the left-hand side is one whole tile, which is again about 10,000 by 30,000 pixels from MIICA, which we call as R1C02, that corresponds to the northwestern zone in the United States. This is the place where there were trees, and most of them are mechanically removal of trees. And those cards are very clear and cut, but then still, when you use MIICA, what we see is we do see a lot of detections. Not all of them are associated with change in vegetation. On the right-hand side, flickering, or there's a GIF animation between the two products. When it says the LF dist is basically our final disseminator project, the final LF disturbance, and the safer is basically the output of the safer product. Now, if those two products are the same, you would not see much of change here, but you do see that they are considerably similar. But there are some changes, and there are some color changes here too. Like if you see that this is the yellow zone, this LANDFIRE does not just use remote sensing. It also it ingests data from people who submit our data. So these are some of the field maps disturbances. The field map disturbances are usually larger in extent than what is spectrally visible. So that's why spectrally, when you see the safer results are a little smaller, whereas the LF dist includes a much larger area. So there are some small changes, but overall, most of you will concur that the large patterns of disturbance and where they are, the big chunk of disturbances that matter, they do concur. So this is a place where it works great. And now the place where it does not necessarily work great is in the shrublands and in the sparsely vegetated regions. What you see again is the MIICA has a bunch of vegetation disturbances that has been detected. But then when you look at the safer, the number of disturbances are fairly low. Although it does pick some of the core disturbances, it leaves us with a feeling that we need to improve a little more. And one of the reasons is the vegetation signal itself is so low. Most of it is barren land with a few shrubs here and there. And if there's a shrub which is lost, the the difference in the spectral signatures between small disturbance in the shrubland is very small. It's within the noise level, which the current process is not able to pick up. But more importantly, for example, this is where the analysts come in picture. Although these are the kind of cases which do not happen, they are not something which is a very frequent occurrence in our data set. But this is something where I'm not even sure how a computer can actually even excel or even come to close to a performance of these kind of detections. So, for example, here in this frame A, we are looking at a DNBR, which is basically the difference burnt area index. If you've been using the remote sensing imagery, you'll clearly pick out some of the dark regions or the places where something has changed to the vegetation. And but the human brain can easily pick out this as a contiguous disturbance, although it does not look very contiguous. And that's true. If you look at MIICA, MIICA has picked up some parts of it and some sporadic, some salt and pepper noise, but it's definitely not picked up this one contiguous disturbance. This, in fact, actually is a road. And that's where the analysts come in, because the SAFER has completely rejected this, and it did not, because it didn't have a good training data. It just selected only parts of it. Whereas that's where the analysts can actually come in and fill in the gaps and say, hey, okay, fine, the entire region, this is one contiguous disturbance, and that can be mapped by the analyst. So long story short, humans have an innate ability to perceive things a little more easier. Our vision is a lot more superior to what the computer can do. So not everything can be completely automated, but we surely have come out a very long way. And I hope when we discuss the discussions after the talk, if there are other techniques which we think we can be implemented to reduce our errors or omissions, we are always looking out for to assimilate newer technologies to make our product a little more quicker and a lot more accurate. So how did we do? Sorry for this really bunch of numbers, and I was hoping not to present it in detail, but to pay attention to the bold numbers in the bottom. I'm quoting overall accuracy from this plane onwards. So the numbers on this side, if they're all close to 100, that means we have done the perfect job. The Holy Grail, this is it. The further away from 100% it is, the further away we are from the Holy Grail. And what you clearly see is, although the overall accuracy is quite high, 96%, in terms of context, we know that only 1% of change actually happens. So even though it is 96%, it seems very high, we would like to get our accuracies a lot higher than this. Our users accuracy and producer accuracy for the undisturbed class is greater than 97%, which is great. Whereas for the disturbance classes, our median accuracies are only about 86 to about 70%. And these are the accuracies which we infer using our own internal metrics. Now, it's a little circular, because although we have used the analyst data to train it, and then we're kind of reusing the analyst data from the next year to infer the accuracies. Nevertheless, they kind of tells us at least the initial accuracy of the raw MIICA product has now been elevated high, that we expect the analyst work to be less. In fact, if we just start looking at the number of pixels that has to be changed, like the number of pixels which has to be reassigned between the raw MIICA and the final disturbance, we can come up with an effort called a relative effort saved, and that comes out to be over 97%. Now, that doesn't mean that we're going to save 97% of the time. It only means that related to the raw MIICA product, the analysts have to change only about 3 or to 4% of the pixels, because the rest are considerably high confidence, which are disturbances directed by the SAFER. The analysts don't start with the raw MIICA product. They do have information from ancillary information which they can rely on. And if you come to Brian's talk, or maybe later we can have if somebody is interested in detail, we can go into that. But they don't start from there. But overall, although this expectation is relative effort saved as theory, in practice we find somewhere between 70 to 90% is basically the effort reduction. But the effort reduction will not necessarily translate in time. So instead of using the same our map disturbances using the LANDFIRE, unless we use an independent data set, it's not going to be an independent accuracy estimate. We have not declared any official estimate right now, so and we'll be putting it up in the Pecora again. LCMAP reference database has an excellent way to judge our accuracies of disturbance mapping. They used expert opinion. They had a panel of experts. They were given about 25,000 points over the conus, which is randomly placed over the entire conus. And between January 1st and December 31st, the analysts went, or the interpreters went, and then they looked for a change or no change. Of course, they had a lot of other parameters, and their primary interest was in land cover. that can be used to map our accuracies as a very independent source. So whatever they maintain as stable or no growth or growth of vegetation, because LANDFIRE does not consider gain in vegetation, and any gain in vegetation is considered as stable or no change. So we're going to consider those stable and growth pixels as no change. And what has changed, which has been interpreted by the analysts as being something mechanically been removed, or there's been a harvest, or the fire, or a structural decline, or a wind damage. Those kind of changes which have been detected by the analysts are labeled as change. So now we have a reference data which we can use to compare our accuracies. The related change proportion is much less than 1%. If you recall from previous experience from the LANDFIRE, the changes are almost 1% of the total landscape every year. And at least in this case of reference data, our proportions are slightly less. On the right-hand side, what we're showing here is the stretch of the entire 25,000 points across the United States, including the red dots and the black dots. The black dots are the places where the changes did not happen between 2015 and 2016. The red dots are the changes that happened between 2015 and 2016. I've just manually increased the font size of those red dots, because if it was red, people like me whose color perception is much less, I didn't even see the red dot. So the red dots does not imply, the size is not implying the area. They're just at one dot, and they represent one Landsat 30 meter pixel. So with that in mind, with using that reference data, we now can calculate the accuracies for the years. So on the x-axis, we have the years going from 2013 to 2016, and we use the LC map data to reduce what's called the kappa. The Cohen's kappa is a very easy way. It's a metric. It's one metric. It's one number. One number going from 0 to 1. 0 means it's a horrible product and nothing matches. 1 means a perfect match, or we hit the Holy Grail requirement. But we clearly see that it is not, it's not 1, but it's definitely not 0. It's fairly high, and is also kind of increased over these years of 2013, 14, 15, and 16. And the standard error, which has its within limits, and we kind of see this trend. We don't expect a 1:1 match, because what I didn't fully mention was with LANDFIRE program, we use a different annual time step to measure. We use the start of the season from the previous year to the end of the season the next year. With the result, our disturbance mapping is slightly, although it encompasses the whole growing season, it is not in sync with a calendar day from day 1 of January 1st to December 31st. So some mismatch is expected, definitely, but definitely some of the trends which we see are expected to be a little more representative. The same thing which you see is a Matthews correlation coefficient. That's again something very similar to kappa. It varies from 0 to 1, and of course we're not expecting 1, and glad that it is much higher. Overall accuracy is something which people often quote. We are consistently over 90, close to 99% overall accuracy. And some of the times where we use what's called the minimum of the users of the producer's accuracy. This is this gives you the least measurement, least accuracies we have, which is basically in the one of the users of the producer's accuracy, and that turns out to be close to about 50% in terms of our mapping in the disturbance class. So we are not that we are fairly well, and because we now have an accuracy measurement, and we now have full confidence in our products. So coming back to a little reiteration of some of the conclusions, we're coming close to the 40-minute mark. Errors of commission and omission, they are the yin and yang. You inflate one, you deflate the other, or you try to minimize one, you inflate the other. So we need to do some kind of an optimal compromise. And all this comes from having what is called a very fixed threshold, a hard-coded threshold that may or may not be valid because of the assumption pertaining to a particular region that may not include the time. A way to bypass them will be to use some kind of a flexible threshold and of course, add more new information. We already have a lot of temporal information, and we see that adding a little bit of spatial contextual information can be useful. But definitely what is more useful is machine learning now has potential. If you combine some of the aspects which we have learned, we can combine all those information, allow the machine to learn, and that actually has potential to reduce the effort. And if you remember the quote from Tom Loveland, all efforts towards reducing the labor and maintaining the high accuracy as well. And I think we're doing quite a good job on the second statement, and we are asymptotically reaching the Holy Grail part of it. I know you guys were bombarded with some of the beginning abstracts with a lot of technical numbers. That was actually the related paper that's coming out, hopefully. I'm still waiting for the review. What we did find is SAFER can safely remove about 70 to 90% of the false detection or the commission errors, where in cases it starts. It significantly increases the kappa. from basically absolute no match at all to a much higher level. So it gives you a very good head start for the analyst. But we did see that analyst review is still needed, and it's an extremely important, crucial part, and that's where focus are. So I think for just as a final statement, the scope for improvement exists, and we are actively looking for newer methods, and hopefully we can have a good discussion. If somebody has some suggestions or comments to make, we do it. As of now, we are happy with our updates and the progress, and we are definitely aiming for an annual updates. So stay tuned, and please do attend the PICORA if you can, and we do have a whole session on LANDFIRE where we'll be discussing this in a lot more detail and will be less of a plain language summary. So that's our LANDFIRE family, the pre-COVID era where we could meet. And with that, I think I'll leave back with this machine learning issues. So those of you who don't want to ask a question, try to answer this of how many puppies and how many muffins you see. I think, Amy, I would like to, if there are any questions.
Yes, we do have a couple in here. Do changes only need to be temporal, or can we also look at other multiple layers or observation from the ground?
I'm not sure I actually understand the question. When you say multi-temporal satellite observations and you say change observed on the ground, I mean, time is always in one way. The change is always temporal. I'm assuming that you're meaning, do we need satellite observations or can we observe from the ground? If that's the question, yes, the LANDFIRE database has a lot of observations which are actually observed from the ground, and they are slightly better because we are there at the place where the things are happening. I'm not sure whether they completely answer that question, but is that it?
There is another one in here. Why are the R scripts being rewritten in Python?
R, I'm not sure if you guys are using it familiar. R has a tendency to be very greedy with memory. R loads everything into the memory. Unlike S+, which is the commercial part of it, we're using R as an open source. R leads everything into the memory, and it does not clear up. The garbage dump doesn't. We can discuss about technical details later. I'm a big fan of R, but unfortunately, R is not good when it comes to really, really large data sets. It's really bad when it passes memory and the memory management, or maybe I'm not very proficient enough. But we find Python does not load up the memory. It loads up only chunks of memory, and it can do a bitwise processing. And that's the reason why we're going towards Python. It's possible that R might have some way to do it, but I'm not aware of it. If you're aware, please do let me know.
That's all I'm showing for questions or comments at this time.
Mm-hmm. I think Tim had asked a question. SAFER has reduced commission errors considerably. Can it do even more? If so, how? And what about omission errors? Does LANDFIRE have a handle on this? Can I answer that question? Nobody else has an answer for that. Okay. SAFER definitely has reduced a lot of commission errors considerably. And of course, it can always be improved. We can have different aspects of training which can be improved. We know the random forest. There are other better machine learning algorithms like if you have a back learning process, there's a whole plethora of machine learning algorithm which can be tried, including CNNs, the convoluted neural networks. Those things can be tried. A random forest is one of the very basic implementations of machine learning, so that can be one very easy way to improve this. And your second question, Tim, about omission errors, actually you're very right. We don't have a very good handle on what our omission errors are. And that's why we expect our collaborators with our other programs with LCMAP. They also do something very similar. So when we start comparing our products, when we start looking at the places where they have detected change, and when we start looking at it, we will start having a handle on omission errors. But as of now, we don't. And hopefully, as collaborations tie up more, we should come up with a much more good metric for how much LANDFIRE is missing. Oh, okay. Sorry, this was not. It was the other chat. I'm still acting like my dad. I'm not very clear about which chat to talk to. Which chat is the presenter's chat.
We do have a request here to repeat what you said about biannual versus annual mapping.
Oh, LANDFIRE, when it started, we know it was a tremendous effort for us. We were hoping for a biannual update. It means we are going to do an update every 2 years. But right now we're doing for every year. We're going to do and we're planning an update every year. So we're going to have we have a 13, 14, 15, 16, 17 map already done. 17 is not released yet. I think Brian can answer this a little more technically when they might be released. But instead of previously we were jumping every alternate years, we are now going for an annual update. I still don't have an answer for the number of puppies or the muffins. Well, let me know if there are any more questions, Amy.
I haven't seen any pop up yet, but if we do receive any, we can certainly send them to you through email.
Sure. And I think I did have put my contact here.
Well, it looks like that's all the questions for this seminar. Thanks very much, Sanath. It was very interesting. And again, LANDFIRE is one of those programs in science that we do here at AROS that affects everybody in the country, and look forward to more progress as the algorithms get better and better.
Yep. Thanks, John.